In this section here, we're going to be talking about area. So if you followed the previous section on integration, and I think it was anti-differentiation, or I believe that's what it was, we're going to be talking about how to utilize that integration symbol by doing integration and finding area under a curve. We're going to start out with some basic stuff here, though, called sigma notation that you're going to need to know. But first I'm going to go to the board and just kind of introduce you to what this next hour is going to be about. Alright, so kind of in a nutshell here, let me draw up, I guess we'll use red for our axis, and let's just do a curve, and we'll just kind of arbitrarily on the screen here do a curve here. And the whole idea is what we're going to be wanting to do is find the area under this curve. So we're just going to be finding this area here, area under the curve. Now, if you've never found area, which I'm sure you probably have at some point in time in your life, let's use something else. Let's say I had a box. Now this is supposed to be a square box here. I'll do my best. And that means that this side is some x and this side is some y. And if we wanted to find the area of this box, well, the area is pretty easy. It's just equal to x times y. Or maybe you might see it as length times width. So that's to find the area of this box. But we notice up here in the top that the height of the box is not changing. As x increases, the height of the box is not changing. Therefore, we could simply just say x times y. But what happens when the height is changing? As x increases, the height, right? This height is changing, either getting increasing and then decreasing. So we can't just say, for example, this is y here. We'll go up to here, and of course here's x. We can't just say that y times x, or x times y, it doesn't matter, that this is going to be now the area of underneath of the what's underneath the curve here, that this is not the area. Of course, we could approximate it. It'd be a rough approximation, I guess. If you did this, you see this piece right here is getting cut out, this piece is getting cut out, and then of course we're adding some to this piece here. So we could do a box to kind of approximate this area under the curve. But what would be even better, and I guess we'll use blue for our XY axis now, it doesn't matter. What would be better is, so let's say we've got our curve here again. If we did smaller boxes, let's say. Okay, so I'm going to try to draw some boxes. But if we did smaller boxes, as you can see here, so let's say that we did smaller boxes. Now what that's going to do is that's going to reduce this error. So you see this little piece right here, that's these little pieces are getting smaller. But what we'd want to do here is we'd want to find the area of that box. We'll call that box 1, and then the area of that box, and we'll call that box 2, and then the area of this box, we'll call that box 3. And of course, to find the area of all the boxes, you just sum up the area of all of the boxes up to the nth box, right? And so that would end up reducing this error part right here, whereas up here we got, we got quite a bit of error. We got this piece here, and then of course what wasn't even underneath the curve. But that's basically where we're headed here. We're going to be summing up a bunch of boxes underneath the curve, and sum, the mathematical symbol for sum is this guy right here. Okay, this is capital, this is sigma. And sigma means we're going to sum up a bunch of boxes here. But if we don't know how to use this, we need to probably look at that first. So that's what we're going to do. Now what we're going to do under sigma notation here, we're going to actually figure out what these things are equal to here. So if you've seen this before, this might just be a refresher. If you've never seen this before, you'll catch on pretty easy. We have, let me get a neutral color here. How about black? Okay. So the first one that we had, I believe I wrote, it was the sigma, and we had I was equal to 1 and 5, and then I out here. Now real quick on the notation. Alright, this is the index down here of the summation. We call this the index. 1 is the lower bound right here, and then the upper bound is going to be 5. Alright, so these are the lower bounds and upper bounds of the summation, and this is the index. And this right here is basically, you'd write a sub I, but we're just writing it. This is going to be the I here. If I had a sub I here, this would be the is the ith term of the summation. But anyway, all right. Well, let's figure out what this is equal to. So what you're doing here is 1. You're going to plug 1 in for I, and then plus, because this is summation. And then we're going to go to the next one is 2 plus 3 plus 4 plus and 5 plus. So instead of writing all of this, we would just do it, we would write it like this, and this would be kind of like the shorthand notation for writing this sequence out. Now we're starting at 1 and we're going to 5, as you can see up here. So that's pretty simple. Now that said, there's actually a formula. There's a formula for this particular one, so we don't have to sit here and go, let's see, 5 plus 4 is 9, right, plus 3 plus 2 plus 1. The formula that we're going to use is I goes to 1 to n, and of course this is our I right here, just like I've got written, except we're going to go to n, so just going out generally. But it's n times n plus 1. You want to make sure you definitely write this one down, over 2. Alright, so in other words, up here you would just take the 5 and plug it in, and 5 plus 1 over 2, and we have 6. 6 times 5 is 30, over 2 is 15. So this sums to 15. Well, let's check this out actually. So this is going to be 9. Let's see, that's 5 and 1, so that's 14, 15. Yeah, it works out. At least it works out for this one anyway. But I'll tell you, it works out for any n. All right. So you want to definitely write that down. In fact, this actually becomes, that's actually handy to know, and all kinds of things going on in life. So write that down anyway. Get it tattooed on your arm or something. Whatever you want to do, I guess. Okay, let's look at another one here. If I had the summation, okay, that's not a very good summation, but hopefully you get the idea. This is going to 4 here, and we have I squared minus 1. Actually, I'm going to write the equal sign down here. So we just plug 0 in, 0 squared minus 1. I'm going to go ahead and keep the parentheses here. Then plus, we go to the next one, 1 squared minus 1 plus 2 squared minus 1 plus 3 squared minus 1, and then of course we're going all the way to 4 now, so 4 squared minus 1. Alright, and so we get, let's see, that's going to be a negative 1, that's 0, that's 4, 4 minus 1 is 3, that's 9, 9 minus 1 is 8, and that's 16 minus 1 plus, and then 4 squared minus 1 is, let's see, 16 minus 1 is 15. Well, if everything works out here, this should all sum to 25. Should sum to 25. Now, of course, there is a formula for this. There's not a formula for I squared minus 1, but there is a formula for I squared. There is a formula for I squared, and I guess maybe what I should do here is go ahead and state that. You'll find these are actually under what are called theorems, but we're just calling them formulas right now. Stated as theorems, and of course we're not proving them. You might find that in a discrete math course, but where they actually prove these. And so this is your I squared, and this is actually equal to n times n plus 1 times 2 to the n minus, or no, plus 1, yeah, and that's all over 6. Now let's just go ahead and try this out. So up here, now of course remember we've got a minus 1 here, okay, so we got to keep that in mind, but that's okay. We're gonna break this up into two pieces because this is the properties of summation notation. Properties are we can break this up. This is I squared minus sigma I going to 0 to 4, and I think I just noticed something, but that's okay, and then minus 1. Alright, now we're going to 0 here, so we need to really calculate the 0th one and then go to the first one, because in our formula down here the way this works is we don't start at 0, we start at 1. See, but that's okay. So we're going from 1 to, what did I say again? 4, yeah, 4. 1 to 4. So I'm going to go ahead and plug 4 in to all this up here and see what we get. So we got 4 times 4 plus 1 times 2 times 4 plus 1, and that's all over 6. So I'm getting 30 over 6. Now this is going from going from 1 to 4 up here. So let's go ahead and write this out. This is I equals 1 to 4 of I squared. Now remember, we still have that very first term, which was I equals 0 to 4 of I squared. And then we've got this one here, which, as you can see, it's just a constant 1, so it's going to be 1 plus 1 plus 1 plus 1 plus 1 5 times, well, starting at 0 and then going to 4. And it's a minus sign actually right here. I'm going to do, so we would have this. What the heck? 1 plus 1 plus 1 plus 1. 1, 2, 3, or think of this, 0, 1, 2, 3, 4. So there's really 5 of them here, right? 0, 1, 2, 3, 4. Alright. And so plugging, I made a mistake here. This is actually the 0th one, sorry. In other words, we're just plugging 0 in for the very first term, 0 squared. Okay, 0 squared is 0, so that's nothing. And then we said this was 30. And then we're subtracting off 1. So we got 30 minus 5, and of course we got 0 over here, right? Plus 30 minus 5, and therefore this is all equal to 25, and I believe that's what we got. I hope that's what we got anyway when we did all this by hand, right? Did the long way around. We got 25. 25. Right. So we had to break this up. We broke this up into 3 really separate pieces, and then this part right here we use the formula. And of course this one right here, we just kind of wrote it out longhand there if you want. Okay, alright, let's look at another one. So this time we're going to look at this one here. We're going to be summing up going from 0 to 3 of I squared minus 1. Wait a minute, we just did that. Never mind. Let's go to the next one here. The summation of k equals 1 to n. So this is a more general case here. We have 1 over n k squared plus 1. So let's work that one out. See if I can make a better summation note sign this time. We have the sum of k equals 1 to n of 1 over n, and then in parentheses times, in parentheses, k squared plus 1. So k, we're starting at 1 here, right, and going to n. But this piece right here, this coefficient, which is not going to be changing at all because we're not going to be plugging anything into this n here. We're just going to be plugging numbers into the k. So what I want to do here is go ahead and just take this out front and just get it out of the way. Get it out of the way. So this was something similar that we did just a little while ago, but I think it was a minus 1, and of course I believe we started at 0 here. But that's okay. Alright, so we're going to write this out as 1 over n, and I'm going to start a bracket here or parentheses. This doesn't matter. We'll start a parentheses. So I'm plugging 1 in. So 1 squared plus 1, and of course I'm going to put this in parentheses plus, and then we're going to go to 2 squared plus 1 plus, and then I'm going to go dot 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 and then do another plus. In other words, there's a lot of terms in here. Between this term and the next term, there's a whole lot of terms there. And then we have, we're going to n. So we just say n squared plus 1. So this might be a little confusing. So we're not actually getting a number out here, right? I'm just showing what this sequence actually looks like if we were to write it out. All right, let's do one more here. Something that we're going to be more likely that we're going to be working with here shortly. We have the sum of I equals 1 to n. This time we're going to use the function f of xi, and we're going to delta x. So we have f of x1 delta x plus f of x2 delta x plus, and once again dot dot dot, meaning there's a lot of terms in there, plus, and then f of x to the nth term times delta x. Now what you could do is you could factor a delta x completely out of this if you want. You can pull the let's pull a delta, or let's write it like this: f of x1 plus f of x2 plus dot 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 plus f of xn, all in parentheses, times delta x. Alright, we're talking about integration, and of course probably like, where's the integration at? But we'll be getting there, don't worry, and we'll be finding the area under a curve. Right now we're just looking at sigma notation. So we're going to look at some formulas here that we've already talked about, but we're going to kind of recap over them real quick, all three of these. If we had the summation of, let's say, I equals 1 to 100, and it was of, let's say, 5. Well, I don't think we want to sit here and go, let's see, what is this going to be? 5 plus 5 plus 5 plus 5 plus 5 plus da da da, right? So we can use this formula right here, which states that I equals going from 1, which is your lower bound, to n of some constant c, and that's going to be this guy right here. And of course this is just equal to c to the n. Now you might have already known that, right? So this would just be 5 times 100, because there's going to be 100 of these 5s that you're going to be adding up. Alright, what if we had the summation of I equals 1 to, let's say, 100 again, and this time it is I. Let's say 1,000. Okay, who's going to want to do this? This is going to end up being, I'm just going to write a few terms out here. So you're going to end up saying 1 plus 2 plus 3 plus 4 plus dot 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 plus all the way up to 1,000. Who's got time to add all that up, right? Okay. And so the best thing to do is we're going to use that formula I equals, which we've already talked about, but we are right, and I should have wrote an equal sign. Well, I guess I could squeeze this in. There's an I right there, and let me rewrite that equal sign right here. Okay, so this is equal to n times n plus 1 over 2. So if we're to use this formula right here, n is going to be our 1,000, right? So this would just be 1,000. And of course we get our handy dandy calculator out, or I guess you could do it by hand if you want. But I think it would be a whole lot faster doing it this way. So whatever this is equal to here, that would be the way to calculate that one. And then this was one that we just got through doing, or this is going to be one like it anyway. Let's say we're going to 20, and it's going to be I squared. So just writing out a few terms here, this would be 1 squared plus 2 squared plus 3 squared plus dot 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 plus all the way to 20 squared. But guess what? There's a formula for this one too. So this is I is going from 1 to n of I squared, and this is going to be equal to n times n plus 1 times 2 to the n plus 1, and that's all over 6. So you would just simply take your 20 up here and you would just plug it in. You would say 20 plus 1. Of course I'll let you work that out. And then 2 times 20 plus 1, and then the whole thing is over 6. So last but not least, let's say we had I equals 1 to, let's say, 10, and this time we had I cubed, right? So this is 10 cubed, or I'm sorry, this is, start over, 1 cubed plus 2 cubed plus dot 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 plus all the way up to 10 cubed, and of course you would add that stuff up. But we have a formula for this one too, and it is just simply n squared times n plus 1 quantity squared over 4 this time, and you would just plug 10 in for n and figure out what this sum is equal to. So we're looking at sigma notation here. We're going to utilize some of these formulas that we just learned, and we're going to show that this left side is actually equal to the right side. So this is the sum of I plus 3 over n squared, and we want to show it's equal to n plus 7 over 2n. Of course, we want to start out by writing that down. So we had the sigma of I equals 1, and we're going to n of I plus 3 over n squared. So since we're starting at I equals 1, as you can see this n squared, we're going to actually rewrite this since this n squared is not changing. I'm going to write it out, so we'll just do baby steps here. I'm going to just take it out of there, and so we have I plus 3. But then again, we can rewrite this again. Remember, part of the properties of summation notation, that is, I can take this 1 over n squared and just get it out of the way to right here. Right. Then we have I plus 3. Now I'm going to even break this up even more to kind of show you what's going on here. We're going to be doing this into two parts here. N equals 1 to n. We're going to do this one plus, and then we break it up some more. N equals 1 to n of the constant. So if you just remember the formulas that we used, right, the formulas that we used, remember what this was equal to right here. Okay? You got to remember what this was equal to. This was equal to n times n plus 1 over 2, right? And then of course this one, remember, was c times n, so this is going to be plus 3 times n. And of course this is, well, we don't want to forget this part out here, and this was n squared. It almost looks like an n cubed there. That's supposed to be a 2. Alright, now what we'll do is do some algebra and collapse this completely down. So this becomes, this piece here is n squared plus n plus, and then I'm going to take this 2, bring it up, so that becomes 6n over 2. And of course we have that 1 over n squared out here. And therefore now we have, so we have n squared plus 7n over 2. We can factor out an n. Seems like we're just going in circles here, but we're not. Over 2. And remember, we've got this 1 over n squared out here in the front. So we can cancel one of these n's out. So we're just left with, we're going to be left with one n down here in the bottom. I should just write an n here. So we end up with n plus 7 over 2n. So finally, all that stuff was equal to n plus 7 over 2n. Let's go back to the top. So we could say that this is equal to n plus 7 over 2n. So that would actually be our formula for this right here if we were plugging numbers in for